Hi everyone. In the previous lectures, we began with our discussion on negative feedback amplifiers. Now, before we go about analyzing negative feedback circuits, I'd like to first discuss very briefly on how to perform additions and subtractions, current and voltage additions and subtractions using some simple analog circuits. Most negative feedback amplifiers will require some form of additions and subtractions. If you see, a general negative feedback amplifier has a quantity which can be voltage or current which is fed back at the input, and they both are subtracted and then fed to an amplifier. So therefore we need to look at circuits, look at how to add voltages and currents or subtract and add voltages and currents. So very briefly, I'll take you through some very simple and interesting circuits which will show you how to perform addition and subtraction of voltages and currents. So first I'll spend more time on voltages because addition and subtraction of currents is quite trivial. All you need to do is just connect the two branches. Okay, so if you connect the two wires, then you will have the currents either adding or subtracting depending on the polarity of the currents. You can add or subtract the two currents. It's the voltage which can be done in quite interesting ways, so which is what I'll be discussing in this lecture. So first, what I'm going to do in this lecture, I'm going to consider voltages V1 and V2 as two voltages, and we'll look at different circuits which can add and subtract the two voltages. So first shown here is a simple averaging circuit. I'm just going to take the average of two voltages V1 and V2, and I have already discussed this. You just put two resistors between them, and if you measure the voltage at the center of the two resistors, that will be the average of the two voltages. And again, this can be very trivially proven using superposition. You can use superposition and show what is the node voltage at this point. Now let's assume I'm applying a voltage delta V and minus delta V. What will be the voltage at this point? If I apply delta V and minus delta V, the voltage at the center is going to be 0, right? It's the average of the two voltages, so therefore it will be 0. Now let's look at this circuit. What I've done here is that I've taken two common drain amplifiers and I've shorted the output of two common drain amplifiers. Now can you tell me what will be the assume V1 and V2 are small signal voltages. What will be the node voltage Vx? What will be the node voltage Vx in terms of V1 and V2? Okay, remember V1 and V2, we don't know the polarity, so we can't say it is 0. So what you will do is you will apply the principle of superposition. So first I'll assume V2 is 0. If V2 is 0, then you have V1 at the gate and V2, the transistor, the second transistor will serve as a load for this transistor, the first transistor. And when you look into the source terminal, if I neglect or not, if you look into the source, the impedance offered by this, what will be the impedance seen here looking up into the source terminal? 1 by Gm, right? It will just be 1 by Gm. So the load resistance will be 1 by Gm. So if you are going to load a common drain amplifier with a load resistance whose value is exactly equal to the output resistance of a common drain amplifier, then what is the voltage gain? So again, you can look at it in many ways. I have already solved how to solve a common drain amplifier. A common drain amplifier can be represented by a Thevenin model given by a voltage source of value V1 and an output resistance of value 1 by Gm. So if I use this model, you can directly see if I connect a load resistance of value 1 by Gm, which is same as the output resistance, then the voltage will be V1, half of the input voltage, which is V1 by 2. So here it is V1 by 2. Similarly, I can assume V1 is 0 and apply V2, and then the node voltage at this point will be V2 by 2. So now add the two voltages, it will be V1 plus V2 by 2. So what you get is an average of the two voltages at this node Vx. See, this is also giving me an average. This is also giving me an averaging. But what is the difference between the two circuits? What difference do you notice between the two circuits? Can you tell me in terms of the current drawn? Am I drawing any current from V1 and V2 in the second circuit? Okay, yeah, small signal. I'm not drawing the second circuit, the input impedance is infinity. I'm not drawing any current. Okay, but in the first circuit, you are actually drawing some current from V1 and V2. Because you are drawing some current from V1 and V2, what will happen if V1 and V2 have finite, if V1 and V2 have finite source resistances, okay, that will also have some impact. If V1 has RS1 and RS2, the voltage at the center will not be equal to V1 plus V2 by 2. It will be equal to V1 plus V2 by 2 if RS1 is equal to RS2. Even if source resistances are same, then it will be equal. But if source resistances are different, then it will not be equal to V1 plus V2 by 2. But in case of the second circuit, what we have shown here, even if V1 and V2 have finite source resistances, it doesn't matter. Even if there is a mismatch in source resistances, your Vx will simply be equal to the average of the two voltages. So that's the difference in the second circuit. Now let's look at the third circuit. The third circuit of interest is what is shown here. Now we will try to analyze what will be the voltage at this point, Vx. Now you can make an assumption R is much greater than your R here, let's assume is much greater than 1 by Gm. If you make this assumption, can you tell me what will be the node voltage Vx? Apply principle of superposition. You can apply principle of superposition even here and solve it. So first assume V2 is 0. If V2 is 0, I am going to ground this terminal. If I am grounding this terminal, what is the total looking impedance? I mean, I'll ignore the current sources now for small signal point of view. What is this node voltage? Let's calculate, let's call this as VO1. This node voltage as VO2. What is this node voltage VO1 in terms of V1? See, remember, make this assumption R is much greater. The impedance looking up here is 1 by Gm. So now this circuit will reduce to something like this. You will have a common drain amplifier with V1 as an input, and the load resistance is going to be R plus 1 by Gm. So that will be 2R plus 1 by Gm, which I can approximate it to 2R itself. If this is 2R, what will be the output voltage here? VO1? V1 itself, right? It will be V1 itself, because your 2R is much greater than 1 by Gm. So I can assume it will be V1 itself. So this node voltage here will be V1. And this node voltage, similarly, VO2 can be shown to be easily, I can show it to be V2. So this is VO1, this is VO1 is V1 and VO2 is V2. So what will be Vx now? So you just have two resistors, the average of V1 and V2, that's it. So that will be V1 plus V2 by 2. So even this circuit gives me an addition average of the two voltages. Okay, that's it. Now we'll look at another interesting circuit. We'll see what does this circuit do for the input voltages V1 and V2. Now this circuit is already familiar to all of us. So this is a simple current biased differential amplifier, a constant current biased differential amplifier. Now if you recall from our previous lectures on current biased amplifiers, we said that there is a very interesting property these amplifiers obey. We said, since there is no small signal current, if as far as small signal is concerned, I is an open circuit. Because I is an open circuit, as far as small signal is concerned, I1 plus I2 will be equal to 0, because I is a DC current here. As far as small signal is concerned, I1 plus I2 is 0. So what can you say about I1 and I2? I1 and I2 will be negative such each other. I1 will be equal to minus I2. Okay, yeah, we discussed about the spectrum and all that, but right now we will look at a much simpler characteristic. So we just now derived, if this node voltage is V1 and this node voltage is V2, what is the small signal node voltage here? We just derived an expression for it. Can I say it is V1 plus V2 by 2? It's the average of the two, which is V1 plus V2 by 2. So if this is V1 plus V2 by 2, what is VGS1? VGS of the first transistor, V1 minus this term, it will be V1 minus V2 by 2. VGS1 will be V1 minus V2 by 2, and similarly VGS2 will be V1 minus VGS2 will be V2 minus the average of the two, V2 minus V1 plus V2 by 2, which will be V2 minus V1 by 2. The VGS here is the VGS1 and VGS2 are negatives of each other. They are 180 degrees out of phase. So now the current I1 here, the small signal current I1 is given by Gm into V1 minus V2 by 2, and I2 is minus of Gm into V1 minus V2 by 2. So now if you look at this circuit, the current, the drain currents in both these MOSFETs are proportional to the difference between the two voltages. They are different, they are proportional to V1 minus V2. Is that right? The currents are proportional to the difference between the two voltages. Now all I need to do, if I want to generate a voltage which is the difference between the two voltages, all I need to do is just take these currents I1 and I2 and push them into a resistor. So if I measure the voltage at this point, let's focus only on the small signal voltage. Can I say the small signal voltage at this point? Let me call this VO1. VO1 will be minus of GMR into V1 minus V2 by 2. The small signal current times R, so it will be minus of GMR into V1 minus V2 by 2. What will be VO2 here? VO2, I can write it as plus GMR by 2 into V1 minus V2. Okay, GMR by 2 into GMR by 2 into V1 minus V2. So now I have generated, if you look at the individual voltages, individual drain voltages, they are already proportional to the difference between the two voltages. And if I take the output differentially, that will be simply twice of this. It will be simply twice of this voltage. It will be, if I take the differential output, VOD differentially, which is V2, VO2 minus VO1, that will simply be GMR into V1 minus V2. So here I have a circuit, even if I take the output single-ended, if I take the output at this node, this circuit will give me a voltage which is proportional to the difference between the two input voltages. So I can directly use my current biased differential pair to generate difference of two voltages. Now I have shown another circuit here. In this circuit, I have two amplifiers connected in series. I have not shown the biasing circuit. The first circuit here is a common drain amplifier. The circuit here is a common source amplifier. So can you apply principle of superposition and tell me what will be the output voltage V0? So first I'll apply superposition to V1. So I'll keep V1 alive and V2 is 0. If V2 is 0, if I neglect R0, if I assume R0 is infinity, what is the impedance looking down? I'm looking into this terminal. What is the impedance? It is R0 of this transistor. If R0 is infinity, that will be infinity. So your source node is floating. If your source node is floating, then the bias current in this MOSFET cannot change. The current in the MOSFET cannot change, which means VGS has to be 0. So the source node voltage will also be equal to V1. Now if I apply the superposition and keep V2 alive and make V1 0, in that case the circuit reduces to something like this. So this is a NMOS common drain amplifier, the upper one. Now what is the load resistance? The looking up resistance, it will be 1 by Gm. You are looking at the source, it is 1 by Gm. So therefore the gain of this amplifier is minus of Gm times 1 by Gm, which will be minus 1. So the output voltage will be minus V2. So if I apply superposition, I'm going to get V1 minus V2. So even this circuit can be used as a voltage subtractor. Now I've designed a circuit which can subtract two voltages. Now we will look at a voltage biased differential pair. I'm going to feed V1 and V2 as two small signal voltages. So you can assume this node is at AC ground. If this node is at AC ground, what will be small signal current I1? That will simply be GM times V1, right? GM, because this is at AC ground, it will be GM times V1. I2 will be GM times V2. If I take the output differentially, okay, if I take the output differentially, I can directly write, see this is positive here, this is negative. So your V0 will be GMR into V1 minus V2. So the currents I1 minus I2 into R, that will be your differential voltage. So that will be GMR into V1 minus V2. So I have discussed another circuit which can generate the difference between the two voltages. We will look at some other circuits and see what these circuits perform. So now what I've done here, it's a current biased, a voltage biased differential pair. I have V1 and V2 connected here. I have shorted the drains of both these MOSFETs. I have short circuited the drains of both these MOSFETs. And I'm asking you, and I've used a 1:1 current mirror. So whatever current is flowing here, I'm mirroring the same current here. I'm pushing it into a resistor. And I'm asking you, what is the small signal voltage V0 here? Remember, this is a voltage biased differential pair. So this node is at AC ground. So the current through this transistor is GM times V1. The current through this one is GM times V2. So the current IX here is simply the sum of the two currents. So V1 plus V2. So now I have generated a current which is the sum of the two voltages. And if I push this current into a resistor, I'm going to get a voltage which will be the sum of the two voltages. So the voltage across the resistor will be the same current GM into V1 plus V2. So it will be GM into R into V1 plus V2. That will be the voltage across the resistor. So what I've done here, what I've shown here is a simple circuit which can perform addition using a voltage biased differential pair. I've used a voltage biased differential pair and generated I've generated a current which is the sum of which is proportional to the sum of the two voltages. So this is something, a well-known idea. So what we said is whenever we want to add two currents, you just have to put the two current sources in parallel. This is something we know already. So all we are doing here is that we are converting the voltages V1 and V2 into currents and then putting the two currents in parallel. That's what we are doing. So we are converting the voltages into currents and then adding the two currents. So that is equivalent to adding the two voltages. So that's what we have accomplished using this. So this is also a voltage adder. Now, if I give you this circuit, V1 and V2 are fed to a current biased differential pair. Now, can you tell me what will be the sum of the two currents? What is the current at this point? Ix. Remember, this is a constant current biasing, right? So the sum of the two currents is always constant. So this current will also be I0. So therefore, this node voltage will also be I0 into R, which is always constant. So it doesn't have any information on V1 or V2. Okay. It doesn't contain any information on V1 and V2. As far as small signal is concerned, as far as the small signal is concerned, it will be 0. I0 is a DC current, so that voltage will be a fixed DC voltage, V0. So for small signals, it will be 0. So this circuit doesn't react to V1 and V2. Okay, I've added the two currents, which is why this is happening. Okay, so keep in mind, even if this current is increasing by delta I, this current is decreasing by minus delta I. So the sum of the two currents is always constant. It's equal to I0. So finally, keeping all this in mind, we will analyze one other circuit. This is a circuit we will encounter when we start discussing about operational amplifiers. So I thought, since we have discussed about additions and subtractions of voltages and currents, it will be an interesting circuit to discuss at this point. What I have done here is that I have here two current biased differential pairs. To the first one, the input is V1 and VCM. VCM is a small signal voltage. To the second one, it is V2 and again VCM. Now I need to find out what is this differential output voltage. For that, I need to know what is this current. So let me call this current as I1 and this current as I2. This current I1 will be nothing but the current through this transistor plus the current through this transistor. So for a constant current biased amplifier, what is this current? What is the current flowing through this transistor? So can I say it will be Gm into V1 minus VCM by 2? The differential, it responds to differential changes, right? So V1 minus VCM into Gm by 2. So it is Gm into, we already derived this right now, so I'm directly writing it now. Gm by 2 into V1 minus VCM. That's the current through this. Now the current through this guy, on the other hand, the current through this guy here is Gm into V2 minus, it is minus of VCM minus V2, but I'll write it as V2 minus VCM by 2. That's the current through this. So what will be current I1? The sum of the two currents. So your current I1 here is going to be the sum of these two, Gm by 2 into V1 minus VCM plus Gm by 2 into V2 minus VCM. So it will be Gm into by 2 into V1 plus V2 minus 2 VCM. So I can write it as Gm into V1 plus V2 by 2 minus VCM. That's your I1. Similarly, I can show I2 will be a negative of this, just minus of this, because we are adding up the other two halves of the currents, so it will be just minus of this. So that's what I have written here. I2 will be minus of this, and your V0 here, your output voltage V0 will be I1 minus I2 into R. You can easily show that it's I1 minus I2 into R. So subtract the two, you will get GMR, and subtract the two currents and multiply it by R, you will get GMR into V1 plus V2 by 2 minus VCM. Okay, I'll discuss about the significance, why are we doing all this when we start discussing operational amplifiers. Okay, this is a much simplified version of a very complex circuit which we are going to discuss at a later stage. So that's it. I'll stop at this point and we will continue with the next lecture.